just have a look at page 2 of your worksheet, June 15 P42. Now, state what is meant by simple harmonic motion. Is a definition question that comes out often. There's both 2 marks. You can actually just copy out the definition from your notes, where you say it's a periodic motion in which acceleration of the body is directly proportional to displacement for a fixed point, and the acceleration is always directed towards that fixed point itself. So this one is 1 mark, where you say acceleration is directly proportional to displacement, and acceleration is always directed towards that point. This is another mark. Okay. Now, if this one feels like a handful to write, there's actually an easier way to write it out if you wanted to. The marking scheme tends to write it in this way. They separate out the definition in 2 separate parts, where the first one you say acceleration is directly proportional to displacement. This is 1 mark. And then after that, they subsequently say that the acceleration and displacement are in opposite directions. This is the 2nd mark. Okay. So if you have write them out as 2 separate sentences like this one would have given you your full marks too. Okay. This one is actually somewhat easier because it's broken down. All right. So you can use either one, the ones from the notes or the ones that's written right over here. Then next thing you do is you look at part B. The variation with time t of the displacement x of 2 oscillators P and Q are as shown in this figure here. The 2 oscillators each have the same mass, so they've already specifically told you that you have same mass here. Use the figure to determine the phase difference between the 2 oscillators. Now for the part here where you are required to determine the phase difference between the 2 oscillators, this one actually refers to your phase difference that you've learned from your AS waves. Okay. So when you wanted to determine phase difference, what you generally had to do was to pick 2 similar points on the waves, which could be crest and crest, trough and trough, and etc. Then after that, what you can do then is to find the difference between the 2 points and compare with respect to 1 cycle. Then the last thing you do is that you express the difference as fraction of a cycle. Okay, so what do I actually mean by this? You can see right now that you have 2 oscillators giving you 2 different waveforms. Your oscillator P is the dotted line. I'll label it as the blue colored line here. And then your oscillator Q is the solid line. I'll label it as the pink colored line right over here. So when you want to determine phase difference between 2 points, you have to pick 2 similar points on the wave, which could be crest and crest, trough and trough, or any other suitable point. So for your case, it will probably be easier for you to pick crest and crest. So I could be picking the crest position on oscillator P and the crest position on oscillator Q. So these are the 2 similar points. And what is the difference between those 2? Based on your graph, it should be 0.2 seconds. The next thing that you want to do then is compare the difference with respect to 1 cycle. This one is easily seen as 1 cycle. If you're just looking at oscillator P, so that 1 cycle, the value of that 1 cycle there is 1.2. Okay, it's 1.2 seconds. So the next thing you want to do is to express that difference as a fraction of a cycle. So in your case, your phase difference is 0.2 over 1.2 cycle. Okay, this is your fraction of a cycle. But your answers usually would want them in terms of maybe radians or degrees. Sometimes you will get radian as your unit, or sometimes you will get degrees as your unit. So in your case, if you had wanted them in degrees, it will be 0.2 divided by 1.2 times 360, or it could be 0.2 over 1.2 times with 2 pi, if you had wanted it in radians. Okay, this one is going to be in degrees. This one is also going to be in radians, because what you know is that one cycle is either 360 degrees or 2 pi radian. Okay, so you would use this one. It's 0.2 divided by 1.2 times 2 pi. Your answer will be 1.05 radian. Okay, for part 2, find out the maximum acceleration of oscillator Q. So this one, since it's an oscillation chapter question, obviously you're talking about simple harmonic motion here. When you're talking about maximum acceleration of oscillator Q, it's already assumed that you're moving in simple harmonic motion. For acceleration, this one is for acceleration at any point. To find your A max, what you know is that A is max when x is x0. In other words, at amplitude. So your A max is therefore omega square x0. Now, for calculations, you normally don't need to bother about the negative. You can just omit it out. We are just interested in the magnitude. So your A max is omega square x0. Now, you do not know omega, but you know there are different expressions for omega, for angular frequency. Omega can either be 2 pi over t, or it can be 2 pi f. For your case, it will be easier to use 2 pi over t because your graph allows you to find period. So oscillator Q is actually the pink colored line just now that I highlighted to you. So one period is actually 1.2 seconds. So your omega square, you substitute as 2 pi over t squared times your amplitude. So it's 2 pi over 1.2 squared, and then your amplitude x0, you can read from your graph, it's actually going to be 3 centimeter. Okay, you read the amplitude as 3 centimeter. Remember to change it to meter, so you multiply with 10 power minus 2. So eventually your final answer would be 0.822 meter per second. Okay, so that's how you find your answer here. Okay, then there's another part to your current question where they ask you to find out the ratio of your maximum kinetic energy or oscillations of Q to P. Okay, how do you find the ratio in the first place? You need to first identify the correct equation to use. Because they're asking you for maximum kinetic energy, from the notes just now, it's already stated to you that KE max is going to be half m omega square x0 squared. Is from page 11 of your notes, where it was mentioned to you that your total energy is your maximum KE, right? So this expression here is actually your maximum KE equation itself. So KE max is half m omega square x0 squared. You use that particular equation here for oscillator Q and P. From there are certain things that you can actually identify as constant. Okay, if KE max is half m omega square x0 squared and it applies to oscillator Q and P, both oscillators have the same mass, because your question already said that they have the same mass, and your angular frequency will also be the same. How do I know that? It's because your angular frequency is 2 pi over t. Okay, it's 2 pi over your period. So if your t is constant here, your omega is obviously going to be constant. You can see from your diagram given that both oscillator P and Q actually have the same period. Okay, this one here is 1.2 seconds, and then after that, this one here is also going to be 1.2 seconds. You will see that it's actually going to give you the same period. So because period is constant, your omega is constant. That's how I can make the conclusion. So right now, if m and omega are constant, that means Ke max is really just proportional to your amplitude square. Your ratio is really just going to be the ratio of your amplitude of Q square to amplitude of P square. So you read from the graph, the amplitude of Q is 3 centimeter. The amplitude of P is 1.7 centimeter. Don't forget to square them, okay? And although they are in centimeter and they are squared, you don't really need to bother to change it to meter because the units cancel off. You can just leave it as it is. You can just take the magnitudes only. So eventually your final answer would give you 3.11 as the ratio. Just like that. Okay. Then you move on to part C, if you're done with that. Now for part C, use your data from B. Data from B is your maximum acceleration that you just found. To sketch on the axis of the figure below, the variation with displacement x of the acceleration a of oscillator Q. They want a graph of acceleration versus displacement. So this one, based on what I just explained to you, if it follows simple harmonic motion, and you compare it to the equation of a straight line, what you're supposed to get is a straight line graph passing through origin with negative radians. Okay, that's the graph shape that you expect to see. But if you look at your question right now, you will notice that your axes are actually labeled with some values. This one is really a hint to you to actually draw your graph to scale with the proper values put in. Another thing that will have already hinted you on that is the fact that they ask you to use your data from B. Data from B, you found out what is your A max. Your A max is actually 0.822 meter per second square, but you can actually probably round it up to 1 SF here to make your graph plotting easier. This one is 0.8 meter per second square. Okay, this one is at x equals to x naught at amplitude position. So your amplitude position for oscillator Q, you found out that it is at 3 centimeter. So you need to kind of like mark out first your maximum acceleration. They'll be at 3 centimeter and negative 3 centimeter. And the value of your acceleration will be 0.8. Now your y-axis does not have any values there. What you can do is that you can just set your own scale. An easy one to set is probably to have 10 small squares as 0.5. So that at 0.8, you are probably going to be at here, somewhere around here. This one is 10 squares. So at 0.8, you are going to be at 16 squares. Okay, so this one would be where you have positive 0.8 and negative 0.8 acceleration. So have that point plotted out here and here. Then you just join those 2 points together. Make sure it passes through your origin. This is the graph shape that we expect to see. Okay. Then next question that we can have a look at is actually page 10. Okay. Okay, page 10 of your worksheet is June 16 P41. Okay, for the first part of your question, they ask you to define what is meant by simple harmonic motion with reference to its displacement. Again, you can actually just use the definition from your notes. Periodic motion in which acceleration of the body is directly proportional to displacement from fixed point, and that the acceleration is always directed towards that point. Or you can always just separate them out, where you say that acceleration is proportional to displacement from fixed point, and the acceleration and displacement are always in opposite directions. Okay, so I leave it up to you not to decide which one you want to use. Now for B, you have a graph of acceleration versus displacement. This time they are asking you to identify from there, why is it that this graph is not telling you that the object is undergoing simple harmonic motion? What they want you to do now is to tell us, why is it that this mass is not undergoing simple harmonic motion? They tell you that the mass is undergoing oscillations in the vertical plane. The variations with displacement x of acceleration a of the mass is as shown, suggest two reasons why your motion of the mass is not simple harmonic in the first place. So just to recap a little, when you have a equals to negative omega square x, the graph shape that you should get is this one. Okay, it's supposed to be a straight line graph with straight line graph that passes through origin. That passes through origin with negative gradient. And another thing to note also is that your graph should be somewhat symmetrical. What we mean by that is that if this one is, say, x naught, this one will be negative a max. And then if this one is negative x naught, negative amplitude, this one will be positive a max. You can see that there's something like a symmetry between these 2 points here. Let me mark it out for you. You look at this point and you look at this point, there is some sort of symmetry between them. Okay, so if you now look at your current graph inside your question, why is this not simple harmonic motion in the first place? The easiest one would be probably to say this. This one is point number 2. The graph is curved, it's not a straight line. If you try to use a ruler and you try to place it on the drawn line here, you will notice that it isn't exactly straight. It curves at some point, like the one that you see here and the one you see here. It isn't exactly straight. Okay, so one reason why this isn't simple harmonic motion is because the graph is curved, it's not a straight line. Okay, and then after that, what's another reason why this one isn't simple harmonic motion? You could say that the maximum displacements and the accelerations are different. If you look at this point here and this point here, the maximum displacement and the maximum accelerations are actually different. They are actually not symmetrical. Rather than saying that the displacement and accelerations are not symmetrical, it's better for you to word it as this. The maximum displacements and acceleration are different. This part here has a maximum displacement and acceleration that's different than the one here. Okay, so this one, maybe I just mark it out. the maximum displacement and acceleration are different. Okay, so this one is wrong. This one, maybe I should just write it. There's symmetry here. I think a proper word to use would be this one. Magnitude of maximum displacement and acceleration are the same. If it's a proper simple harmonic motion graph. Okay, so this is another reason why your existing graph is not SHM, because maximum displacement and acceleration are different, in addition to it not being a straight line. Now your question here just requires you to state the reason. They didn't really ask you to state and explain. There's no state and explain here. If there's a state and explain, in addition to stating why is it wrong, you have to kind of like explain why. So let's just say if you say that for point number 2, the graph is curved and it's not a straight line, how does this explain to you that it's not simple harmonic motion? The graph being curved actually tells you that your acceleration and displacement are not proportional to each other. This is the explaining part. And then for the first point here, where you say that the maximum displacement and accelerations are different, why is it that this one is not simple harmonic motion in the first place? The actual reasoning for that is because in simple harmonic motion, both sides of the graph should have equal maximum displacement and acceleration. Or you could also say it's same, okay? Same maximum displacement and acceleration. Okay, so that is for this part. Then you move on to part C. Now for part C, you have a block of wood that's floating in the liquid as shown. The block is displaced vertically and then released. The variation with time t or the displacement while the block from its equilibrium position is as shown in figure 3.3. This is the one that you see here. So from there, calculate out the angular frequency omega of the oscillations. All right, so your block is oscillating up and down, and they plotted out a graph of displacement from equilibrium versus time. They then want you to find out what is your angular frequency omega. So angular frequency is always just going to be either 2 pi over t or 2 pi f. So you just find out your period. The easiest way to look at is this part here. This is one period. It's actually 0.8 seconds. So just substitute in as omega equals to 2 pi over t. It's 2 pi over 0.8. You're going to get 7.85 radians per second. Just for your angular frequency then. Okay. This is pretty straightforward. Then after that, next part is calculate the maximum vertical acceleration of the block. So they want the maximum acceleration here. So based on what we've just done earlier just now, without going through the derivation again, we know that maximum acceleration is really just the angular frequency square multiplied with your amplitude. The derivation of it, like the ones that is being shown above here, this is actually not necessary to be shown. The moment they ask you what's maximum acceleration, you can just use this straight. The moment they ask you what's maximum velocity, you can just use Vmax equals to omega x naught straight. There's no need for you to like show the derivation. Okay, so here you already found out the omega, the angular frequency from the previous question. Your amplitude here is 1.5 times 10 minus 2. This one is read from here. Okay, this is your amplitude that you read. If you look at your graph right now, your amplitude positions are actually here, 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 and here. So why is it that I specifically choose this point as my amplitude position is because you're finding A max, you see. Amax is omega square x naught. If you want to find the max value for acceleration, this one must be maximum amplitude. So this one is where you get your maximum amplitude. Because you want the largest value of acceleration, you must use the largest value of amplitude available. You cannot just simply pick any point here. So you use that value. Remember to change it to meter from centimeter. You will get your answer as 0.924 meter per second square. Okay, then for part 3, your block has a mass of 120 grams, and then the oscillations of the blocks are damped. When your oscillation of blocks are damped, that simply means that your amplitude decreases with time. Okay, your amplitude decreases with time. This is due to energy loss. We'll cover more about damping in the later part of the chapter. Okay, for now, we just focus on the calculation part of it. Now here, your oscillation of your blocks are damped. Find out the loss of energy of oscillations of the block during the first 3 complete periods of its oscillation. How much energy has been lost now for the first 3 periods of its oscillation? So if you look at your graph now, this one is one oscillation. This is another oscillation. And then this is another one too. So this 3 is your 3 oscillations. They want the energy loss for the first 3 complete oscillations. So meaning to say they want the energy loss between this point and this point. These are the 2 points that you want to consider. You want to find out the energy loss between these 2 points. So total energy, as mentioned, was your KE max, which in turn work out to half m omega square x naught square. So you want to apply this particular equation onto this point here and onto this point here. Then you find out the energy loss. Okay, let's just say that this one is E1, this one is E2. Your energy loss is really just E1 minus E2. Okay, so here you get half m omega square x1 square minus half m omega square x2 square, which can be factorized out as half m omega square x1 square minus x2 square. So what is your x1 here? Your x1 here is 1.5 centimeter. Your x2 here is, I believe, 0.9 centimeter. So sub in everything, then you should be able to get your answer. Did it give you the values of the rest of the variables? I believe they give you the mass as 120 grams in the question itself. Your omega is something that you already found in part 1 of your question. So all you just needed to find out further was your amplitude only. Okay, when you say that your energy loss is half of 0.12 times 7.85 square multiplied with the amplitude of the first part minus off with the amplitude of the second part squared, and then giving you this answer here is 5.32 times 10 power minus 4 joules, just like that. The workings that you see here is actually just something like extra background info. You don't necessarily need to write this, okay? But I do suggest that you kind of like write a general equation out now. You don't need to like write out a derivation or anything. You just need to write out a general equation telling the examiner what are you trying to do here. before you sub in your answer. Okay. In my case, I use x naught 1 square minus x naught 2 square. But here I just put an x1 and x2. It doesn't matter, okay? You can use whichever form you like. It's just that my labeling sometimes changes with time, right? So if you're okay with this, we just do this other short question on page 9 first. Right, this is March 2016 P42. You have an object of mass 80 grams that oscillates with simple harmonic motion. The variation with time t of the displacement x of the object is as shown. Find out the amplitude and period of the oscillations. This one will be very straightforward. Your amplitude is this one, which is going to be 1.8 centimeter. And then your period is going to be this one, which is going to be 0.3 seconds. Okay, right. And I think I've mentioned this to you before. Final answer is 2SF minimum. So for my case, I shouldn't write it as 0.3. I should write it as 0.30 seconds. Okay, this is your amplitude and period. So last part here, use your figure and your answers that you have just found in A to calculate the kinetic energy of the object at time t equals to 0.19 seconds. Here, they're not asking you to find maximum kinetic energy or anything like that. They're just asking you to find kinetic energy at a particular point, specifically at t equals to 0.19 seconds. If you look at your graph, where is 0.19 seconds? 0.19 seconds is actually over here. This is 0.19 seconds. And it is actually corresponding to amplitude of 1.2 centimeter, negative 1.2 centimeter. So they want you to find out right now, what is the KE here at this point? The general equation for KE at the point is half m omega square x naught square minus x squared, which is this one. Okay, so you're going to use this one here in your workings. You need to first find out what is your x at 0.19. What is your x at 0.19? It's actually 0.12 centimeter at t equals to 0.19 seconds. You sub this one in, you already know the rest of the values. You already know your mass, you already know your angular frequency, you already know your amplitude. You can now find out your KE. Okay, so this is your working. Your angular frequency wasn't exactly given, but you can find it from your period because omega is 2 pi over t. That's what you're doing here. Then you're finding out the omega. So after that, you square your omega, put in the value of your amplitude, square it, put in the value of your displacement at 0.19 seconds, and also square it. And also change it to meter also. Because all your values are here in centimeter, you need to change it to meter. So it becomes 0.018, 0.012. So once everything is done, you should get your final answer is 3.16 times 10 power minus 3 joules. Okay. Your mass is given here, 80 grams. All right.